everyone. In today's video, we're going to be doing lesson 9.5, which is going to cover absolute and conditional convergence and divergence of power series. But first, before we get started, I would love to do a couple warm-up problems, reviewing some older material. So in the first warm-up, I want to know what is the approximation of the value of sine of 1 obtained by using the fifth degree polynomial about x equals 0 for sine of x. And I'm noticing now that I really don't need this right here. What is the approximate value for sine of 1? Okay, so first we need to find the fifth degree Taylor polynomial about x equals 0. So if you recall, if I'm taking a Taylor polynomial about x equals 0, another word for that is Maclaurin polynomial. And we learned a bunch of Maclaurin superstars. One of them was for sine of x. So recall that sine of x is equal to the sum from n equals 0 to infinity of negative 1 to the n, x to the 2n plus 1, all over 2n plus 1 factorial. Therefore, if I want to know the fifth degree Taylor polynomial or fifth degree Maclaurin polynomial, I would need to take this out till I get an x to the fifth. So let's see, if I write a few terms out, if I plug in n equals 0, I would end up with just an x. If I plugged in an n equals 1, I would have a negative x cubed over 3 factorial. And if I plug in an n equals 2, I would have plus x to the fifth over a 5 factorial. So here it is. I need to, in order to keep my equal sign, I need to put minus dot 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 here. But here I can see is my fifth degree Taylor polynomial. So I know sine of x is approximately equal to x minus x cubed over 3 factorial plus x to the fifth over 5 factorial. So now if I want to know what the value of sine of 1 is, I can simply substitute 1 in for my x values. So I'd have 1 minus 1 over 3 factorial is 6, plus 1 over 5 factorial is 120. You're welcome to leave your answer just like this. You're welcome to simplify it and leave it as a fraction. You are welcome if you have a calculator and they ask you to give me the approximation for this. Let me tap it in really quick. You would get 0.842. For the AP exam, you want to make sure you round to the nearest thousandth. That's always the directions they give you, so you might as well practice that. So there is the first problem in our warm-up. Let's move on to the second problem. Now this problem deals with what we learned in section 9.4. So it says, which of the following series will converge? So let's take a look at the first one. I notice here in the first one, if I take the limit as n approaches infinity of n over n plus 2, that would be equal to 1. And so therefore, this series is going to diverge by the nth term test. So recall the nth term test said, if I take the limit as n approaches infinity of a sub n for the series, and I do not get a 0, that would mean that the series is going to diverge. So then let's look at problem 2. I'm actually going to skip it. I see that cosine of n pi, and I'm just going to move right on to number 3 because 3 I'm looking at and it looks really easy. So let's take care of that one. So I notice number 3 is a p series where my p value is 1. And therefore I know that this series is going to diverge by the p series test. Let's just take care of that one while we're here. All right, now let's go back to number 2. It looks like it's going to be a little more work. So I have the sum from n equals 1 to infinity of cosine of n pi over a n. So I believe we dealt with this in our notes. So think from 9.4. So think about what this means. If I plug in n equals 1, here I'd have cosine of pi, which is a negative 1. Then if I plug in 2, I'd have cosine of 2 pi, which is a positive 1. Cosine of 3 pi is a negative 1. Cosine of 4 pi is a 1. 5 pi negative 1, 6 pi 1. You see the pattern. It's going to be alternating between negative 1 and 1. So I'm going to rewrite this series. It is equal to the sum from n equals 1 to infinity of negative 1, and it looks like I need to raise to the n. Since I'm starting with n equals 1, it started out with a negative, so I need to make sure if I'm keeping that 1, I need to make sure that I start with a negative, and n would do that. Perfect, over an n. All right, so now since I have an alternation here, I'm going to start with the alternating series test. So if you remember, the things that you need to check for an alternating series test is you need to make sure that if you ditch the alternation and just consider your rule without the alternation, that needs to be decreasing every single term. So the limit as n approaches infinity of a sub n needs to be equal to 0, which it does, and the terms have to be decreasing every single time, which this one will. So therefore, this passes the alternating series test, and I know that this will converge by the alternating series test. But now let's consider absolute convergence. So consider the sum from n equals 1 to infinity of the absolute value of negative 1 to the n all over n. Consider that. Here, that would ditch my alternation, and I would just be left with 1 over n for my rule, which I know diverges by the p-series test. Therefore, while series number 2 does converge by the alternating series test, it does not absolutely converge. Therefore, it is also called conditionally convergent. All right, so just to recap, in number 2, 1 is divergent, 2 is convergent and conditionally convergent, and 3 is divergent. Now we're switching gears, and we are going to be discussing a power series, not just a normal series. So in a power series, what's changing is you have a variable. So if you look at number 1, sine of that in the warm-up, sine of x equals the sum from n equals 0 to infinity of negative 1 to the n, x to the 2n plus 1 over 2n plus 1 factorial. That's a power series because we have a variable. And if you look at warm-up number 2, those are just series. In 9.4, we were only dealing with series, learning all of those convergence and divergence tests. Today, we are switching gears, and we're going to add in that element of a power series. So for a power series, centered at x equals c, exactly one of the following conditions is going to be true. The series converges only at x equals c, which is its center. And note that all power series are going to converge at their center. Like, this is very important. All power series converge at their center. If this is the case, and the series converges only at its center, that means its radius of convergence is equal to 0. So that was that capital R that I know we have discussed, but haven't clearly defined. So that would mean radius of convergence is 0 if it only converges at its center at one point. Or part 2, the series could converge for all values of x. And if that is the case, then the radius of convergence is infinity. That is true for several of our superstars that we learned. I believe e to the x, sine of x, cosine of x, those all converge for all values of x, therefore their radius of convergence is infinity. And then the last one, the more interesting one. There exists an r greater than 0, such that the radius of convergence, that the series converges for x minus c is less than r. This is the notation we see a lot. And then it diverges when the absolute value of x minus c is greater than r. If this is the case, that would mean that the radius of convergence is this value of r. And the corresponding domain of c minus r, c plus r, is called the interval of convergence, or the domain of that power series. So what we'll do is we're going to start with a ratio test on these. The ratio test, recall, is really nice. because whenever I take my limit as n approaches infinity of a sub n plus 1 all over a sub n, I know that whatever that limit is, the whole series will converge when that limit is less than 1. So it builds in this notation that I've highlighted in green for us. So let's take a look at some examples. So I want to know for what values of x this series absolutely converges, conditionally converges, and is divergent. So the second I see a power series, I'm going to make this big so I have lots of space. The second I see that this is a power series, I know I'm going to start with the ratio test, which says that the limit is n approaches infinity of a sub n minus 1, or a sub n plus 1, so this would become negative 1 to the n plus 2, x to the 2 times n plus 1, which becomes 2n plus 2, all over 2 times n, which again is 2n plus 2, divided by a sub n, so that's multiplying by the reciprocal, and now I need to clean this up, so I'll have the limit. It's n approaches infinity. Let's first take a look at my negative 1 to the n plus 2 over negative 1 to the n plus 1. If I were to take those like bases, that would mean I would subtract n plus 2 minus n plus 1, which would just leave you with a negative 1 to the first power. So I'm really just left with a negative 1 from that. Then let's look at my x's. I'd have x to the 2n plus 2 over x to the 2n. Doing the same thing I did with the negative 1s, I'd be left with an x squared. And then what I like to do, because the limit is as n approaches infinity, I like to isolate all of the, like the polynomial type n's. Anything left with an n, I should say. So I have 2n over 2n plus 2. What that allows me to do is really think about what the limit as n approaches infinity is doing, because the negative 1x squared is now just hanging out. It's going to be left over. So when I take the limit as n approaches infinity of 2n over 2n plus 2, I would get 1. I know that the absolute value of negative 1 is just 1, so therefore my limit is just the absolute value of x squared, and that is all that's left. Therefore, this power series is going to absolutely converge when the absolute value of x squared is less than 1. So think about what x values you can plug in that would make this statement true. I can plug in negative 1 is less than x is less than 1. And that would give me, oh, I lost my t. And that would make that any absolute value inequality true. If you wanted to think about what the radius of convergence is here, the series has a center of 0. And I know that this absolute value equation here, where this is my center, would give me that interval negative 1 to 1. Therefore, here is my radius of convergence, and my radius of convergence is 1. I know that wasn't asked for in this problem, but we might as well go ahead and discuss it. So I know that this series is absolutely convergent on this interval, but the question is, what about negative 1 and 1? Like, is it convergent or divergent at those endpoints? That's the new piece that I'm going to need to check. So what we're going to do is we're going to check each endpoint. So let's check negative 1 first. I'm going to have to come over to the side and do that. All right, so let's check x equals negative 1. To do this, I'm just going to plug in negative 1 for x. So I go to my original series. I'll have negative 1 to the n plus 1, and then negative 1 to the 2n all over a 2n. So notice I'm just subbing in right for x. So now consider what this is. If I have negative 1 to the 2n, well, think about this. This is always just going to be 1, because 2n will always be even, and so negative 1 raised to an even power will always be 1. So now this can simplify to be the sum from n equals 1 to negative 1 to the n plus 1 all over 2n. So notice at that endpoint when I plug in the x value, it becomes a problem from section 9.4 where I'm just wondering if this thing converges absolutely or conditionally. So now if I'm thinking about this on its own merit, I can see that this thing is going to converge by the alternating series test. But then if I consider absolute convergence, that would take away that alternation. And that negative 1 to the n plus 1 would just become a 1 over 2n. And this is going to diverge by p series, because I can pull out the 1/2. Let me go ahead and write that. This is equal to 1/2 times the sum from n equals 1 to infinity of 1 over n. So there I see that divergent p series. So therefore, at x equals negative 1, the series converges and it conditionally converges. Now the next endpoint that I need to check is positive 1. So let's check x equals 1. So when I plug in 1, I would have the sum from n equals 1 to infinity of negative 1 to the n plus 1, and then just a positive 1 to the 2n, which is just going to be 1 all the time. So I'm not even going to write it, over 2n. And here I can see I get the same exact thing that I had here. So there's no need to do the work again. I know that this is going to converge by the alternating series test, but it is conditionally convergent, because if I take the absolute value of the series, that will not converge. So now let's put all of this together for example 1. So where is the series absolutely convergent? It is absolutely convergent when 1 or negative 1 is less than x is less than 1. But it's convergent, just plain old convergent, from negative 1 is less than or equal to x is less than or equal to 1. It is conditionally convergent at these two endpoints, negative 1 and 1. And then it's going to be divergent anywhere that it is not convergent. So if I just look here, the convergent and divergent, they have to complement one another. So it's going to be divergent from negative infinity to negative 1, not included, union 1 to infinity, where that 1 is not included either. If you want to, you're also welcome to use this notation, like instead of using these inequality notations, you could write your absolutely convergent interval, negative 1 to 1. You could write convergent, hard bracket, negative 1 to 1. Set notation is going to have to be used for the conditionally convergent because I have only those two values, but it just is your preference on however you prefer to write these. Let's take a look at example 2. So it's the same type of problem, just a different series. So since I see the power series, I'm going to go ahead and start with my ratio test. So I have the limit as n approaches infinity of 10x raised to the n plus 1 all over n plus 1 factorial times n factorial all over 10x raised to the n. And now we'll start cleaning that up. So first I'm going to look at anything with an x. So I'll have the 10x to the n plus 1 over 10x to the n. And when I clean that up, I just get a 10x raised to the first power. And nothing left in the denominator. And now I'm going to look at those polynomial n's because I know those are really going to drive that limit. So if I have n factorial over n plus 1 factorial, remember that n plus 1 factorial is n plus 1 times n factorial. So these would cancel, and I would just be left with 1 over n plus 1. So when I take that limit as n approaches infinity of 1 over n plus 1, I would get a 0. So no matter what x value I plug in here, I multiply it by 10, then I'm going to multiply it by 0, this limit is always going to be equal to 0, which is always less than 1. Therefore, this series is absolutely convergent for all x in the real numbers. That would mean that its radius of convergence is equal to infinity. And now when I come over here to fill this in, where is this absolutely convergent? For all real numbers. Where is it convergent? For all real numbers. Where is it conditionally convergent? Nowhere. So I'm going to write the null set, or you can write none if you want. And where is it divergent? I'm going to write the null set, or you can write none. So that one wasn't too bad at all. Let's look at example 3. So here I finally have one that is not centered at 0. You can see just on site that the center of this power series is 3. So let's go ahead and start with my ratio test. So the limit is n approaches infinity of x minus 3 to the n plus 1 all over 2 times n plus 1, which is 2n plus 2, times 2n over x minus 3 to the n. Let's clean this up. I'll have the limit as n approaches infinity. The x minus 3, so we'll cancel out, leaving me with just with 1 x minus 3 in the numerator. And again, I like to put my polynomial n stuff with an n over to the side. So I have 2n over 2n plus 2. So now I'm isolating this limit. And this limit will be equal to 1. So therefore, my big limit is equal to the absolute value of x minus 3. And I know that the series is going to absolutely converge when the absolute value of x minus 3 is less than 1. And notice this notation here. I have x minus my center is less than my radius of convergence. So I know my radius of convergence for this series is going to be equal to 1. Now let's clean up this inequality to get my interval of convergence. I have negative 1 is less than x minus 3 is less than 1. And when I add 3 across my inequality, I have 2 is less than x is less than 4. Now my next step is to check my endpoints. So I need to check x equals 2 and x equals 4. So first let's plug in 2 to my series. When I do that, I'll have the sum from n equals 1 to infinity of negative 1 to the n all over 2n. Again, this looks very familiar, doesn't it? I know that this is going to converge by the alternating series test, but then I need to consider its absolute convergence. So when I take the sum from n equals 1 to infinity of the absolute value, I would have just a 1 over 2n. And I know that this diverges by p series, because we've already done it here in these notes. So therefore, at x equals 2, it is convergent and conditionally convergent, but not absolutely convergent. Now let's check x equals 4. So here I have the sum from n equals 1 to infinity of 1 to the n, which is just going to be a 1, all over 2n. And here I've done this work here already. This is going to diverge by p series. So therefore, it's just divergent here. And now we can summarize over here. So I have all my work shown. So in the summary, where is this absolutely convergent? Well, only from 2 to 4. I'm going to use this notation this time. Where is it convergent? Well, that would be from 2 included to 4 not included. Conditionally convergent is only at x equals 2. And where is it divergent? Remember that convergence and divergence integrals need to complement one another. So not integrals, intervals. So I have negative infinity to 2 not included, union 4 included to infinity. If you really prefer the other notation, again, you can write this as 2 is less than x is less than 4. You could write this, I'm running out of space, is 2 is less than or equal to x is less than 4. if you prefer, you're definitely welcome to use either notation. So that is lesson 9.5.